going to continue to look at volumes today, just kind of rehashing what we've looked at already. If you have one function that you're trying to rotate around an axis, then you just do pi r squared with that one function as your height. If there's multiple functions involved, then you want to find the difference of those two circles. So you're doing pi r squared minus pi r squared, where this is the radius that's further away from the axis, and this is the radius that's closer to the axis. If you're going around the y-axis instead of the x-axis, then it just same functions, but you want to get the functions in terms of y, and also make sure then that you take your limits from the y-axis here, not the x-axis. All right. So let's look at this problem. They want us to find the volume of a solid obtained by rotating the region R enclosed by these two curves, and we're going to rotate it around the line y equals 2. What's different about this problem than the ones we've done so far? Well, all the other ones we've always either rotated around the x-axis or y-axis. Now we have a line that's different here. We're rotating about a line that's not an axis. So what we need to do then is we're going to have to adjust what these radiuses become then, because your radius distance is now going to be different. So what happens here? Well, here's the graph of these two functions. So if we were to graph out these two functions, we get this, and we've looked at this one before actually. But we rotated it around either the x-axis or y-axis. What if we now rotate it around the line y equals 2? Well, where is that line here? Well, the line y equals 2 is a horizontal line, because the slope here is 0, that goes through 2. So on our picture here, here's 1. So 2 would be up, if we continued this y-axis up here, y equals 2 would be somewhere up here. So that line looks like this. So that's the line now that we want to take and rotate around up there. So what's going to happen now is, since we're doing that, that line is where we have to find our radiuses from. So we need to know what's the radius distance from that new line up there to our different curves here that we're doing. So here's kind of a better picture of it. So what we're going to do here, here's our line y equals 2. We have to find what are those distances. What's the distances from those radius? Because when we spin it around, that's what it's going to look like. So going back to our picture here, what we're going to need to know is, what is the outside radius? What's the distance on our picture from the line we're rotating to that curve that's furthest away? Well, the curve that ends up being furthest away here is this one. That one's further away from the line we're rotating around, so that's the one we got to pick first. Because remember, we do our kind of our outer radius minus our inner radius. Well, what are we going to call that length right there? Well, from doing these problems before, we know that the distance from here to here is the distance of the height of that function, which would be x squared, because that's the graph of this one. But that still doesn't tell us what to call this upper line. But we know something else. We also know that the distance from here to here is going to be 2. So the distance of this top line then from the line we're rotating around to that function would be the difference of that. That would be 2 take away the distance of x squared. Here's kind of this on this picture, so same idea here. We know that this distance here is 2. The distance from here to here is going to be x squared. So that means the distance of this outside radius here would be 2 minus x squared. We're going to do the similar thing now with that inside radius. So the inside radius, we know that this is again a distance of 2. The length from the axis to this point is x. So then this amount right here, this total distance here would be 2 minus x. And so those become our two radiuses. So now when we're setting up this volume equation, what's it going to be? Well, let's see, it's going to be the volume integrated from, let's go back to our picture here, from still 0 to 1, okay? Because this is one we're doing in terms of x here. We're rotating around something parallel to what the x-axis would be. So we want to keep it in terms of stuff with x. So we're going to integrate this from 0 to 1 of pi r squared minus pi r squared. What's the bigger radius or longer radius in this one? Well, you can see from the picture, 2 minus x squared, that's the radius that's further away. So that's the one we want to do first. 2 minus x squared, that radius squared minus pi r squared again, but with the closer radius, and the closer radius is this one, 2 minus x squared dx. Again, if you want to factor out that pi, because we got pi in both, we can do that. So now we just have to integrate what would this be. Okay, now we've been doing these enough where you guys kind of have gone through enough of these that you should be able to go through and find that on your own. Remember, if you were to do this one on your own, you would need to simplify both of those first. And what I mean by that, if you were going to try to figure out what this integral would be, you would want to make sure you'd multiply out 2x squared times another 2 minus x squared and FOIL that out. Same with over here, you'd have to FOIL that out and then simplify that and do all that and then find antiderivative. But we've done enough of these that I think let's use calculator to figure out what this integral is going to come out to be. So on the calculator to do that again, you're going to want to go to your math button here, find your integral one, number 9 here, the FN int. Okay, select that one. Enter our limits here, 0 and 1. And then I'm not going to include the pi on this one. We'll just make sure we multiply that pi back. Otherwise, it'll be tough to understand what answer we're trying to get here. So now let's go parentheses 2 minus x squared. And then close the parentheses, and we want that amount squared minus. And we'll do our other radius here of 2 minus x. Close that parentheses, also squared. And then finally, make sure we get our dx in here. Hit enter, and this should be the amount that. Now, that to get the exact answer, do it as a fraction by hitting your math button. And it looks like the volume here comes out to be 8/15. Make sure, though, that you do multiply that back by pi, because we didn't enter the pi in the calculator, so it'd be 8 pi over 15 units cubed would be the volume there. Okay, so if you have a line that's not an axis, that's how you got to kind of go through and treat it. All right, let's look at this next one. Find the volume obtained by rotating the same region now around the line x equals -1. X equals -1, that's going to be a vertical line because x equals 1 is not a function. So over here, somewhere wherever we have -1, that line's going to look like this. And what we want to do is rotate this around here. Okay, so similar thing now. We want to figure out what is the volume, and we need the bigger radius minus the smaller radius. Since this line is parallel to the y-axis, we're going to want to do everything in terms of y on this one. So like we did on some of those other ones, we want these functions in terms of y. This top line's easy because that's just going to be the same thing. That would be x equals y. This one, we'd have to take the square root, so this bottom function is x equals square root y. So those would be our two functions. Now we want to figure out which one, what's the radius further away and which one's the closer one. The one further away here, if you start at your line that you're rotating around, you want to keep going till you hit the one further away. That one. That's the one we want to start with. So now we got to figure out what's that distance. Well, we know this distance right here from the line, from our axis to there, that's the distance of square root of y. We also know that we should also know this distance. The distance from there to the axis would just be 1 because it's the distance from 0 to -1, which would be a distance of 1. So what is that total distance going to be? That total distance would be, adding those together, would be 1 plus square root of y. Okay, here's another way of seeing it here. So we know this distance is 1. We know this distance here would be square root of y, and so that total distance here would be 1 plus square root of y. Okay, now we want to do that same thing with the inner radius. So the inner radius, for the distance from here to here would be y. The distance from here to here would be 1. So the total distance would be those added together, 1 plus y. All right, so now when we set this integral up to find the volume, our volume would be the integral. Now remember, this one is y, so we want to come up with our limits from the y-axis. This would be, the y value is 0 here. The y value here is 1, so it'd be from 0 to 1 of pi r squared minus pi r squared. What's the one furthest away? We said that one is 1 plus square root of y squared minus pi r squared. Again, what's the inner one? The one closer was the 1 plus y. Pi r squared. So we got to make sure we square that amount. And this one would be dy. You can factor out the pi again. So if we do that, now we got this. Let's use our calculator here to again simplify this. Now your calculator won't have y on it, but that's okay. You should be able to put this one in the same way. Just instead of y, just enter it as x. It'll come out to be the same amount. It won't change anything about the value of this. So select integral. We're doing it from 0 to 1 here. Again, I'm going to leave the pi out, just otherwise we get a nonsensical answer that we won't know, because pi would make it a decimal number that we don't know how to evaluate. Now put in these two here, parentheses, 1 plus square root of, we'll use x instead of y, it'll be fine, squared. Whoop, didn't hit the over button here, so let's get rid of that. Gotta hit over to get outside of that. Didn't get that out of there either. All right, hit over, over. All right, close the parentheses. Now outside of that, and then hit squared. And then we want to minus the other one, which is parentheses 1 plus y, but we'll use x instead, and that quantity squared, and then get our dx in here, and we should get it. All right, so that's the answer there. Now, sometimes this may happen. If you try doing math fraction right now, I don't believe this is going to do anything. No. Sometimes the calculator, it uses a process of approximating again to do these. you're not always going to get the exact answer. My assumption here would be that this is trying to evaluate to just 0.5 because we see it's 0.5 and then a bunch of zeros and they throw some other numbers there at the end. So my guess is this does simplify to just 0.5 or 1/2. If it's an exam and you want to make sure, you could always go through and multiply this out and find the exact solution like we've looked at before. So this comes out to be 1/2 or 0.5, and then again, make sure you get your pi with that. So 1 pi over 2, or you can just write that as pi over 2 units cubed. All right, let's try one more. Find the volume of the solid attained by rotating this region bounded by the curves, and they give us a bunch of curves here, and the line x equals 1. So first thing we're going to want to do is graph that out. So let's see if we can graph this. So on a graph here, let's come up with a picture of what this looks like. So we get the lines y equals x, so that would be a line that has a y-intercept of 0 and a slope of up 1 over 1. So that would look something like this. That's the line y equals x. We got the line y equals 0. That's a horizontal line through 0, so that would be basically that line. We got the line x equals 2. That's a vertical line here. And the line x equals 4 would also be a vertical line. And we want the amount in between that, so we're looking at this shaded region right there. That's our region that we want to rotate. Okay, so we got a picture of what that looks like. Now let's get the line we're rotating around. The line we're rotating around is the line x equals 1. It's also a vertical line. So that's the line x equals 1. That's the one we want to rotate around. Okay, so now we got to come up with what is the functions for this one. Now this one, you got to look, is that line that we're rotating around parallel to the x-axis or y-axis? It's parallel to the y-axis. That means this one, when we're doing this, we want everything, we're going to need everything in terms of y here. So we want to come up with equations that would give us this in terms of y. So all our equations here could be written as that. This one, you got to think of it just x equals y. Okay, so we want to rotate that around. We want to come up with what's the radiuses from that. Now let's start down here. On the bottom part, what is the distance from the line we're rotating around to the point furthest away? Well, that distance, right, it would be right there. So what is that distance? Well, here you could just count it out. That would be a distance of 1, 2, 3 spaces there. So the volume on this one would be the integral of just our furthest radius, which would be pi times 3 squared, minus, now what's the distance to our inside radius? What's the distance from here to here? Well, that distance is just 1 space, so that would be times pi times 1 squared. Okay, now you got to be careful on this one. Are those two radiuses the same throughout? The inside radius the outside radius looks like it's always going to be that same amount, because even if I draw it up here, the furthest I go away, I always hit that line x equals 4. The problem though is that our inside radius isn't always 1. Up here, our inside radius changes. Now it goes till it hits that line. So we are going to need on this one 2 integrals, because right here our inside radius switches from one to another. So we got to split this up. We need 2 separate integrals in order to do this one. So we're going to have to take whatever this integral gives us minus whatever this top integral is going to be. So let's go back to our first integral and complete it. We need the limits on there. What are the y values basically kind of this bottom square down here. And remember, because this is parallel to y, we need our integral values to come from the y-axis. So this one looks like it starts at 0 and ends at 2. So this would be from 0 to 2. Now our new integral would go from 2 to, looks like if where it ends up here would be at 4. So this one's going to be from 2 to 4. And now we got to figure out that kind of that triangular piece. What's that distance going to be? So the outside radius on this one still looks like, right here, looks like a distance of 1, 2, 3 spaces. So that one's going to be pi times 3 squared minus, what's that inside radius going to be? Pi times what here? Well, that radius now becomes a little bit different. That one is, what's the difference from that line to this function here? So what we know is the distance from our function to the axis, that function is, or that distance is y. But we don't want that distance. We want the distance just from the line we're rotating around. So what's that distance going to be called? Well, to do that, we're going to have to kind of think through this one. What's the distance from here to the line? That distance is 1. We got that distance all the way from here to here. That's y. So what is the distance then just from here to here? That would be the difference of those. So what we would call that would be y take away 1. So if you took that whole distance of y and minus to the 1, this would be y minus 1. And so here, our radius would be y minus 1 squared. And these should both be dy, not dx. All right, so now you want to evaluate and see what you get here. Again, if you want to enter this one in the calculator, do some very easily simplifying here. We could, on this top one, pull the pi out. So it's going to be from 0 to 2. And this one, we could simplify that. We'd end up with what's 3 squared minus 1 squared would be what's left. That's 9 minus 1 is just going to end up being just 8. So this is just going to be 8 dy minus, and let's pull the pi out on that bottom one too. This would be the integral from 4 to 2. And this one's going to be 3 squared, or 9, minus y minus 1 squared dy. All right, so now let's use a calculator to evaluate both of those, and then we'll see what our final answer is going to be. So this one you are going to have to do as 2 separate ones here. First one, 0 to 2. This one should be easy to enter, of just 8 dy. In this case, we'll use x. So area of that part ends up being, is just going to end up being 16 minus. Now let's see what this second one is going to evaluate to. So calculator again. Hit it a little too fast there. So this one's going to be from 2 to 4, and then we got 9 minus the quantity y minus 1, but we'll use x here with our calculator. Close that parentheses, don't forget the squared, and then we want the dx, even though it's dy, we're using on the calculator dx. So that amount's going to be 9.33333. Now let's subtract those. Okay, so we know this is going to end up being 9 1/3 here. So what is that subtracted? And then we got to multiply our pi back to there to get the final answer. So what's 16 minus what we just got there? And then let's make this into a fraction. And it looks like we get 20/3 there. So our final answer then should be that the volume is 20 pi over 3. And that would be our final solution. So that that amount should be our, oh, sorry, it won't be our answer. I screwed up here. When we're doing this, we should, our two integrals here are both correct, but we want to be adding we want to add the amounts from this one to this one, not subtract them. So we should be adding these two integrals here. So, sorry, my fault. Let's back it up. Should be a quick fix here. All we got to do is add these two instead of subtract them. So what's 16 plus 9 and 1/3? We get 25 and 1/3. Now if we turn that into a fraction, we get 76/3. Sorry about that. 76 pi over 3. Units cubed would be our answer. Okay, so the reason, again, we want to add these two is we're taking these and separating. If we looked at what the picture of this looks like, once we revolve it around that line, there is a little bit of a gap here, so it would kind of be this kind of cylinder shape. The inside of this would kind of look like this, but there would be this kind of inside hole in there, kind of like that when we spun that around. So kind of like a funnel type shape on the inside of that. So it looks something like that. Okay. I want you to try these new problems out here. See what you get doing this.